Welcome to Zebra Aurora Vision Studio. In this tutorial, we'll take a closer look at the Detect Features tool available in Zebra Aurora Deep Learning. We'll learn when to use this tool, how to work with it effectively, as well as go through the process of marking features, training our deep learning model, and testing its performance. The Detect Features, or DF in short, is one of the deep learning-based tools available in Zebra Aurora Deep Learning add-on. It is used to detect pixel-wise regions corresponding to defects, or, in a general sense, to any image features. This can be anything from cracks on solar panels to roads and rivers in a satellite image. Detect Features excels at dealing with irregular defects which are hard to analyze using traditional machine vision methods. It does not require the user to be proficient in traditional machine vision algorithms or coding. Instead, it offers powerful capabilities enclosed in a user-friendly model editor. Even though the tool requires supervision during model training and manual labeling of features, it can also mark the features semi-automatically, helping us to save a lot of time and effort. In this tutorial, we'll build a sample deep learning application which will detect irregular defects on pipe fitting threads. As mentioned before, such irregular defects are very hard to work with using traditional machine vision methods, and that is exactly where our deep learning tools come into play. Our program will be fairly simple, utilizing just a couple of tools: film strip from the image acquisition section of the toolbox, as well as two deep learning tools, deploy and detect features, both available in the deep learning section of the toolbox. To start with, we need to acquire some images first. For the purpose of this tutorial, we'll use images from one of our examples. By default, deep learning examples are hidden in the dataset list. To activate them, we need to click Show All Dataset option. We can see the full list now. Let's choose the thread dataset. Now, we've got the images from this dataset loaded into the film strip control. Let's add the film strip filter to acquire them. The filter is grayed out, and there is a warning message. It's because film strip works only in offline mode. Let's switch to it now. Once our acquisition is active, we can proceed to the next step. When working on a new program, it's usually good to start from previewing the images we'll be working with. Let's do it now and check where the defects are and what do they look like. As we can see, defects on these samples differ from each other a lot. Let's continue and check some more images to see what we're going to work with. We're going to add our deep learning filters now. We'll start from deploying the deep learning model into memory, which will speed up our program greatly. This can be done by adding the deploy filter into the initialize section of our program. If this section is hidden, you can expand it by clicking the sections icon. Okay, it's visible now. Next, we'll just drag and drop and choose the filter variant. In our case, we'll pick the Detect Features variant. Please note that this step is not mandatory. Our program would work just fine without the deploy filter. It is, however, a very good habit to preload the model, which speeds up our program and helps to keep the memory clean. Alright, we can add the main deep learning filter now. Let's add the Detect Features tool. The two question marks indicate the missing mandatory inputs in image and in model ID. Let's connect them now. Okay, we're almost done, but still missing one thing. We need to specify a target directory for our deep learning model. Here, I'll just copy-paste the path, but you can choose it in the File Explorer too. This directory will contain all the different models, so make sure it's in a good location. When you're done, simply click OK to open the Deep Learning editor. This is where all the magic happens, so let's get to work. Instead of going through every single item available in the editor, we'll assume a bit more practical approach, explaining the most important things in the process. The first step is adding all the images used in training our model. We simply click the Add Files from Directory icon and select all the files we need. The other three tools allow us to import or export images with masks, or to delete selected items from this set. You can find all the training and test images used in this tutorial in the Program Data/Aurora Vision directory on your hard drive. Okay, we've loaded the image set now. Let's browse it really fast. You've probably noticed that there is a small train label next to every item. It indicates that the image is part of the training set. In other words, it will be used for training the model. If we click this label, it will change to test, indicating that this item now belongs to the model test set. Simply speaking, test images are not used for training the model, but for testing it afterwards and generating model statistics. Let's move this image back to the training set though, to keep things simple. The next step is marking the features in all the images. Here, we are looking for some visible damage of the thread, similar to this one. For marking, we will be using a set of drawing tools like brush, rectangle or polygon. And if we make a mistake, there is the eraser tool to help us out. Let's mark some features now. We'll be using the brush tool for this job. We can change its size freely to suit our needs. For now, let's keep it relatively small. While marking, it is usually good to extend the mask outside of the marked feature by 1 or 2 pixels to give the neural network some extra context to work with. In many cases, this approach will give us better results compared to when we mark the features very accurately. Features, or defects if you like, have to be marked on every image. This process takes some time, but Zebra Aurora Vision Studio comes with a couple of tools that can help in speeding up this task. These tools will be covered in a separate tutorial though. For now, let's proceed to the next step. Okay, we've got all the defects labeled now. Let's check a couple of images to see what they look like. Please note that we skipped showing you the whole labeling process since it is pretty straightforward. You've probably noticed that some images have no features labeled. It is because there are no defects present and the inspected parts are considered to be okay. It's usually good to include a couple of images with no defects both in the training and test set to give the neural network some extra context and teach it what does a good sample looks like. Now, let's proceed to tweaking the training parameters, which is the final step required before training our model. Training parameters window is located in the bottom left corner of the screen. Let's resize it a bit to get a better view. We will not discuss all the parameters in detail in this tutorial. If you would like to know more about them, please refer to our technical documentation. You can also check the tooltips which explain all parameters briefly. The first two parameters are responsible for the complexity and memory usage of our neural network. Basically, the more complex the defect, the higher the network depth is required. In our case, since we're looking for a pretty simple defects, we can even reduce this value to save some memory. Let's set it to 0. Patch size refers to the size of the inspection window. The rule of thumb is that it should be large enough to fit the defect and some of its surroundings. In our case, the default value of 96 should be okay, but let's check it on another image. As we can see, the defects fit the window with some extra margin, so we're not changing it. The next two pre-processing parameters are pretty straightforward. Just quick note that downsampling is often used when we have large, complex images that take up a lot of memory. We'll leave everything at default here. The augmentations are used to artificially generate additional training images. Using them, we can often get a working model, even if we have just a couple of sample images to work with. For more information, please check the tooltips or refer to our documentation. Let's tweak them a bit really quickly. We definitely want to use rotation angle and image flipping, since the inspected parts appear in different orientations. Setting the angle to 180 tells the software to generate some extra samples rotated by a random angle from this specified range. We also use translation and image scaling to generate some extra samples in which the object is moved or resized slightly. All these parameters are often used for objects that vary in size or have a changing position and orientation. The following 5 parameters introduce some other transformations, including noise, blur, or luminosity changes. Usually, it is enough to tweak them just a little bit to add some spice to the final training dataset. Let's do it now. Last but not least, we've got the stopping conditions, which tell the software when it should stop training the deep learning model. Here, by default, we've got the validation accuracy set, but we can add another condition that will limit the training to 60 minutes. The training will stop whenever one of these two conditions is met. Okay, we're all set. Let's save our model and jump to the Region of Interest tab. When we're done with labeling the features, we can proceed to setting regions of interest. To switch to the Region of Interest editor, simply click its icon in the Workflow section. We now got access to a couple of different Region of Interest related tools. We can change its base shape to either rectangular or elliptical, and then simply adjust it in the preview window. If we want to revert to default settings, we can also do it with a single click. Regions of interest can be set for each image individually, or we can set one common region of interest for all images in our dataset. This is particularly useful when we have images with constant object placement. However, in our case, we will keep the default setting for all images. Let's revert to them now. We are now ready to start the training. We do it by clicking the train icon in the bottom right corner of the window. Please notice the green light indicator in the bottom left corner. It indicates that the deep learning service is ready and running. If it was red, we would get a prompt window asking us for permission to start the service before commencing the training. Okay, we're all set. Let's train our model. When the training starts, the progress window will pop up. Here, we can track the progress chart as well as other parameters like training and validation accuracy, elapsed time, or memory use. We can also change the chart settings so that it'll show only a couple of last iterations, whole training progress, or automatically pan and zoom when the chart grows. Let's set it to whole progress. For the sake of this tutorial, we've limited the training time to 10 minutes. We also won't be showing the whole training progress in this video, but instead we'll jump straight to the end of training and final results. When the training is complete, the progress window will automatically close. We're now back to the Deep Learning editor and we got switched to the Training Results tab. Notice that there is a number next to every single image in the image browser on the left. This value is the image score. Basically, the higher the score, the better. Image scores are also presented graphically as heat maps in blue, yellow, red colors palette after using the model to evaluate an image. The color represents the probability of an element belonging to the currently selected feature class. In other words, it depicts how certain the neural network is that something in the image is similar to what we labeled during model training. Here, our heat map is red. It means that according to the neural network, it is very likely that these parts of the image represent what we have labeled as defect. We can also compare the heat maps to what we have marked by toggling the class labels on. Or, if we want, we can turn the heat maps off completely. Let's check a couple of images to see what other results look like. Now it's time to test our model in the wild. Let's save it and go back to the program editor, where we'll run the program and evaluate a set of test images. We're back to the main window of Aurora Vision Studio. The images in the film strip have not been used in model training. As mentioned before, they belong to so-called test set, which means that our model will see and evaluate them for the first time using what it has learned during the training. Let's display the heat map in the preview now. To do so, we just drag and drop the OutFeature1 output into the preview window. As we can see, the results are pretty impressive. The model successfully identifies even the small defects in the bottom part of the inspected element. Let's see how it copes with the rest of images and check whether it identifies a good sample or not. This one looks like it has no defects. Let's zoom in and check the results. As expected, there is no heat map present, which means that the model works as intended. This also concludes our program and this basic tutorial. Thank you for watching and see you again soon. This concludes our tutorial. If you want to learn more, please take a look at our technical documentation available at Zebra Aurora Vision Developer Portal. You can find links to the sections of the documentation relevant to this tutorial in the video description below. Thank you for watching. For more information on Zebra Aurora Vision software products, visit us at aurora-vision.zebra.com.